Alright, so now let's try to illustrate these rather abstract definitions with a little more concrete example. So consider a bag that contains one red and one blue cube. Okay, so very simple example. Suppose we randomly select two cubes with replacement. So we're going to select one cube, put it back, select a second cube. The two cubes we select are called the sample. Okay? The sample space in this case is the set RR, which means we get a red and a red, or we get a red and a blue, or a blue and a red, or a blue and a blue. Okay? And we're going to assume that each of these outcomes is equally likely, which seems reasonable. Okay? Now we're going to define the random variable x to equal the number of red cubes in the sample. So here an outcome is a collection of cubes. The random variable is we're going to take that those cubes and return the number of red cubes in the sample. Okay. Now to illustrate what that means, let's look at x as a function. X is going to take an outcome and return a real number. So for instance, one outcome is RR. If we plug that into our function x, we're going to get the real number 2. Right? Because there's 2 red cubes in that outcome. Okay? Another outcome is red-blue. If we plug that into our function x, we get the output 1. X of blue-red is 1, again because there's one red cube. And then lastly, x of blue-blue is 0. Okay? So this random variable x can take on 3 different values, 0, 1, or 2. Okay? Now, let's look at calculating a few values of the associated probability mass function. So little f of 0 is, by definition, the probability that capital X equals 0. Well, capital X can equal 0 only when we get the outcome blue-blue. What's the probability of blue-blue? Well, there were 4 outcomes in our sample space, and exactly one of them did we have a blue-blue. And so the probability is 1/4. So f of 0 equals 1/4. Another value of x is 2. So to calculate little f of 2, that is by definition the probability that x equals 2. X equals 2 only with the outcome of red-red. Probability of red-red is also 1/4 because there's only one outcome in which we get a red-red. And 4 possibilities, so 1/4. Now, the last value of f is a little more complicated to calculate. F of 1. That is, again, by definition, the probability that x equals 1. X can equal 1 when we get the outcome red-blue or blue-red. The probability of each one of those is 1/4, so 1/4 plus 1/4 is 1/2. So there we have the different values of our probability mass function. Okay. Now let's describe the distribution in the 3 different forms. So again, the distribution is just a description of these different values of the PMF. Here we have the distribution in the form of a table. Across the top row, we've got the values of the random variable 0, 1, and 2. Across the bottom row, we have the associated values of little f, 1/4, 1/2, and 1/4. Okay. Now, sometimes we like to draw a picture of that, and we do that with what we call a probability histogram. So across the horizontal axis, we have the different values of x, 0, 1, and 2. The vertical axis, we have the values of f of x, and we have 1 bar for each value. The height equals the value of f of x. And so there we go. This histogram tells us the same thing as the table, just in a different form. Now lastly, we can find a formula. And here's a formula. F of x is equal to this. And so if we plug in 0, we're going to get out the number 1/4. If we plug in 1, we're going to get out 1/2, so on and so forth. Okay. Now exactly how we found this formula isn't terribly important. What's only important is that it works. If we plug in 0, we get out 1/4. We plug in 1, we get out 1/2. We plug in 2, we get out 1/4. And so those are 3 different ways of describing the distribution of this particular random variable. Now, whenever we describe a probability mass function, we should make sure that it satisfies the properties of a probability mass function. So let's make 3 observations here. Number 1, note that all the values of this PMF are positive. So that means it satisfies the first property of a PMF. Second, if we add up the values of f over the range of x, this right here denotes that we're going to add up the values over the range in x. So that's by definition f of 0, f of 1, f of 2. If we add those up, we get exactly 1. So that means this function satisfies the second definition of the second property of the definition of a PMF. Now, the third property isn't really something that we need to verify. It's really a description of how we use the probability mass function. Okay? So to illustrate that, let's suppose I want to find the probability of getting 1 or 2 red cubes in this random experiment. So in terms of the value of the random variable, it's the probability that x equals 1 or x equals 2. Another way of describing it is the probability that x is in the set 1, 2. So by the third property of the PMF, we calculate this by adding f of 1 plus f of 2, and we get those numbers from our distribution, 1/2 plus 1/4, which is equal to 3/4. So there's a 75% chance that I'm going to get exactly 1 or exactly 2 red cubes. Now, there was a definition, the generic definition of a probability mass function and a random variable. In this next definition, we're going to define a specific type of random variable that has a specific type of distribution. It says let x be a discrete random variable with k elements in its range. So k is some positive whole number. So we could have 5 elements, 12 elements, 15 elements. X has a uniform distribution, or is said to be uniformly distributed, if its probability mass function is 1 over k for each x in R. Okay? So what's important here is that k is some whole number, so 1 over k is a constant number. So we're saying here it's uniformly distributed if its PMF is constant. Think about what the word uniform means. It means like everything's the same. And that's really what we're saying here. The probabilities of all these different values are the same. And so to illustrate this, let's look at this simple example. Consider the random experiment of rolling a fair 6-sided die. So we're going to roll it once. So our sample space is 1, 2, 3, 4, 5, 6. So we have 6 elements in our range, or in our sample space. Okay. Now let's let the random variable x denote the number of dots that land on the side that lands up. So in other words, x is just really another name for our outcome. Okay. Now the probability, now all of these outcomes are equally likely. So the probability that x equals 1 is 1/6. Probability that x equals 2 is 1/6. Probability x equals 3 is 1/6, so on and so forth. So our PMF is 1 over 6 for each x in our range. So in other words, x has a uniform distribution. So a uniform distribution is rather simple because everything is equally likely. There's only one value to our probability mass function. Now, our next definition, we're going to define something similar to the PMF, but we're going to call it the cumulative distribution function, abbreviated CDF, is defined to be this. We call it capital F instead of lowercase f. Our input we're going to call b rather than x. And it's by definition the probability that x is less than or equal to b. So it's not the probability that x equals b, it's the probability that x is less than or equal to b. So now by the third property of our probability mass function, we can calculate that probability by simply adding up values of our probability mass function over all values of x less than or equal to b. Okay. So to illustrate this, let's look at this example. And this is really an example that we've seen before back in Chapter 1. Consider the random experiment of rolling 2 fair 6-sided dice and calculating their sum. Let the random variable x denote this sum. Okay? So down here in the corner, we have all of our possible outcomes. Here's our outcome from the first die, the second die, and then here's their sum. And so these values here are the values of our random variable. We see they take values between 2 and 12. And here in this table, we describe the distribution. X goes from 2 to 12. There's only one outcome in which the sum is 2, so this probability here is 1/6. The probability that x equals 3 is going to be 2/36 because there's two outcomes there that equal 2, so on and so forth. Okay. Now, let's calculate the value of capital F of 4. Capital F of 4 is, by definition, the probability that x is less than or equal to 4. Okay? Less than or equal to 4. So x is less than or equal to 4 means that x equals 4 or 3 or 2. So by the third property of our PMF, we calculate this by adding up f of 2, f of 3, f of 4. And so we just add up these three numbers right here, and we get 1/6, and we're all done. Now lastly, we're going to define two numbers that we call the mode and the median. Okay? The mode of a discrete random variable x is the value of f is the value of x at which the probability mass function is maximized. Okay? The median of x is the smallest number m such that these two probabilities are true. So the mode you can think of as kind of like the most likely value of x. F is a measure of how likely the different values of x are. We want to maximize that, and so that's the mode. The median is, you kind of almost think of it as like the number right in the middle. It's not really the number in the middle, but that's kind of a way to think about it. So we need a number such that the probability that x is less than or equal to that number to be at least 0.5, and the probability that x is greater than or equal to that number to also be 0.5. Okay. So let's go back to this example 221, which is the first example from this section. And that random variable had the distribution given in the form, in table form here and graph form over here. Now the mode is equal to 1. That's the value at which the PMF is maximized. So that's the highest point here. So that's all there is to finding the mode. You look for the high point on the graph, and you're all done. Now, the median is equal to 1, and we know that that's true because if we calculate the probability x is less than or equal to 1, so that's x equals 1 plus x equals 2, 1/4 plus 1/2 is 3/4. That's bigger than a half. And the probability that x is greater than or equal to 1 is the probability x equals 1 plus the probability that equals 2, and that's also equal to 3/4. So because both of these probabilities here are greater than a half, that means that our median is equal to 1. And furthermore, 1 is the only value of x for which these two probabilities are at least 1/2. So that's why our median is equal to 1.